So in the last class, we have defined cosine similarity and we have started the discussion on how we can use this cosine similarity to score a given document for a given query. And using that, how can we have the impression of a ranked list or a ranking or a rank retrieval. So in sum, the cosine similarity between two vectors x and y is this, where I hope you can remember this is basically the dot product of the vectors x and y. And in the denominator, it is basically their length normalization factor, which is basically the L2 norm of the individual vectors, right? Here, this summation or these three summations all are basically done for all the dimension. Basically, if the vector is m dimensional, it will be basically from I to m. So do this and as well as this. So how can we use the cosine similarity as a ranking module to rank a document, to rank a set of documents? So to rank a set of documents, as we have discussed, we need to assign some score to all the documents in the collection. And after doing that, we will be sorting them in the descending order, and based on the descending order, we will be selecting the top k or top maybe 10 or 100 documents as the most relevant one. So the score of the document for a given query will be basically, if we are following the vector space similarity or the cosine similarity, it will be basically the dot product of the vectors associated with the query and the document. In the denominator, it will be their L2 norm again, and the summation would be performed over the vocabulary size. That is, let's say in the vocabulary there are say 5 terms, say A, B, C, D and E. Now what we need to do is so if let's say for query and for document the corresponding vectors are say 1 1 0 0 0, that is the query is AB, the document is say 0 1 0 1 1. So what we need to do is we need to just using this cosine similarity, only this portion will be selected, because for this component, that is whenever we will be performing this summation for I equals to 2, which is basically the second component or second dimension in this 5-dimensional space, we will be getting this as a non-zero value, particularly a 1 value, and based on that we will be basically performing, or we will be basically getting the corresponding cosine similarity, and we will be accordingly scoring the document. So I hope it is clear why this, what is the implication of this vector or the size of the vocabulary here. Now, in general, we can say this component is the weight associated with the query, and this component is the weight associated with the document. And as this is a summation, basically this is the weight of the query term I in the query and weight of the query term I in the document. So this is what I have written here. Here, see that earlier the summation was on the entire vocabulary. Now it has been reduced to only the query terms. How we are actually gaining from this? Because as we have seen, if a term is actually a query term, or if a term out of the all the vocabulary terms, if the term is occurring in the query, then only it is being checked. I mean, essentially, we need to check for these two queries, whether these two queries are present in the document or not. We don't need to check for all the five terms in the vocabulary, because we know that the non-query terms are not actually this component will be basically 0. So the product will be 0. So we can simply ignore them. That's why this thing can be reduced to the summation over only the query terms. And the weight of the query term, pardon my miswriting here, it should be small q here, similar to this here. Okay. Now this scoring following the cosine similarity can be used as the ranking module in the vector space model. The algorithms for doing that is something like this. What we need to do is we are defining a function called cosine ranking, where we are passing the query. Note that this query can be containing multiple terms. We are only passing this. This function is initializing a scores array, where the length of the array is basically the number of documents in the collection. That is, for this query, theoretically we need to assign the score for each of the document in the collection. So if the collection containing 1 million document, essentially we need to assign some score to all those 1 million documents for that query. So that's why I'm initializing a list or an array of the length of the number of documents in the collection and initializing it to 0. That is, this will be, I'm basically indicating this as initializing an array of size n. All of the indices are filled with 0. Okay. Then what I'm doing is I'm initializing another variable, another array, which is length, which is basically contains the length of individual documents. So as there are n documents in the collection, this length n will be containing all the lengths of the, note that both of these should be having the same length, and this length array will be having the individual length of the individual documents. Now this length will be needed for doing this L2 norm or the thing in the denominator. So one question to you is how we can actually initialize this. How? Think of it a little bit. This is a very important concept. I mean, it can be a very important one from the point of view of the upcoming mid-semester exam. Okay. Now, what I am doing here is I'm applying a for loop where I'm traversing for each query term in the query. I'm calculating the weight, this one basically, the weight of the query term in the query to get this, right? Which is basically, we can simply say, if we are considering the term frequency as the weight, we just need to check the term frequency of the query term in the query. Most of the cases, which will be 1. That is, this is basically, let's say the the query is say IPL auction 2022, then The number of query terms are 3, IPL, auction 2022, and the individual term frequency of the individual query terms are 111. So most of the cases, if we will be considering this TF, then we will be getting a 1 value here or a unit value here as the weight. Then what we need to do is we need to write a function given a query term, which will be basically giving us back the posting list. That is all the documents containing that query term. Now for each document in the posting list that we have retrieved, we need to compute this score. So earlier at the beginning the score will be 0, and the here the weight will be the query weight. Sorry, this is not the query weight, this is the query weight, which we have already calculated. Basically this factor, and this factor is basically the weight of the query term in that document, this factor. Again, we can, if we are, while making the inverted index, if we are storing the term frequency of the individual of the query term in the individual document, and if we are using that term frequency as the weight of the term in the document, then we can simply get that from the posting list, right? And sorry, it will be for each. Then after this, we will be ending up with the scores list initialized to some documents will be having non-zero values. Now note that if it is say IPL, auction 2022, first the query term will be IPL, then auction, then 2022. For IPL, we'll be getting a posting list for which we'll be changing the document score for some of the documents. In the next iteration, the value of key will be basically auction. For that, it will be basically this PL will be basically the posting list of auction, and based on the presence of the document in that posting list, we'll be changing the scores of some of the other documents. And finally, for 2022, we'll be getting another posting list, and we'll be changing or modifying the scores accordingly. Now, up to this, what we are basically finalized with is basically this part. That is, so up to this, it is basically the dot product of the query vector and all the document vectors. Let me denote it by capital D. So this is basically all the document vector. Now what we need to do is we need to apply this length normalization. And we have already initialized this. I hope you can understand how we can do that. This is a small task for you. This length is basically containing the length of individual documents. Then what we need to do is we need to apply this normalization factor to all the documents. Now note that this factor is actually common for all the documents, right? I mean to say is the ultimate target of information retrieval is ranking, right? Based on the scores, we will be ranking. So if a set of documents, if the score of the set of documents are divided by a constant value, say m or not m, so say if they are divided by a constant value, say phi, the ranking will be remaining the same, isn't it? So that's why this thing can be excluded from the effective computation where the ultimate target is ranking. So essentially what we'll be doing is we'll be only using the L2 norm, equivalent to the L2 norm, that is the length of the document, not the query. But we can actually do this, but it's also true that we can also neglect it or just ignore this. So the length D, this array is already containing the length of all the documents. So what I'm doing here is, so this is basically for each D in the posting list. Now note that I am not doing this for all the documents. Now this posting list, I am considering it to be containing all the, it is basically, I should have written it as a capital PL. This posting list is basically the union of the posting lists that we have got from here. Now, what is the advantage of doing this rather than doing this? What is the advantage? In this case, the number of documents or this division would need to be computed for all the documents in the collection. But for a given query, the number of documents which are containing the query terms will be relatively less, right? So this will be actually reducing the computation time of dividing the score by the document length. That's why it is actually advantageous rather than doing this. Finally, we need to sort the score, which is basically the normalized score, normalized cosine similarity. We need to return the top k document with the highest score. Okay. All right. Now let's focus on how to actually calculate this, or what are the different approaches that we can apply to get the individual weights. Here in this example, I am only considering the weight. You can see I am only considering WQD, WQQ. I am not saying what is the function, what is this W function is all about. Is it a TF? Is it an IDF? Or is it a TF IDF? Let's discuss that, which is the essence of, or which is basically all about this term weighting. The first approach is a very basic one. We can simply consider a binary indicator. So weight of a term T in D will be 1 if T is present in D, otherwise 0. Similarly, weight of the term in Q will be 1 if T is a query term, otherwise it will be 0. So this is a very simple one, which is basically, in which approach the similarity is basically the word overlap. We have discussed this while discussing the Boolean retrieval. The second approach is an advanced one over this. So what we'll be doing is, instead of applying a binary factor, we'll be using unweighted factor. So as a weight, what we will be doing is we will be using the term frequency of the query term in the query as well as in the document. Earlier it was 1 1, or if it is 1, then only we are considering it. If it is 0, we know if either of it is 0, then the resultant factor will be 0, because that term is not present either in the query nor in the or in the document. So the product will be resulting into 0. So that's why essentially this can be computed over the intersection of Q and D. Here the same thing, but we are not actually considering a binary value. We are considering the TF, the term frequency of the value of the term in the document or in the query. So this term frequency is considered as the weighted version of the binary factor that we have discussed in approach 1. Now consider, so here for a given document D, for a given query, the score of the document will be basically summation of the term frequency of the term in the query and term frequency of the term in the document, where the term T is theoretically computed for all the terms in the vocabulary. But as we have said, if the term is not occurring in the, so the length of the vocabulary might be say 1 million or more than that. But the length of the query will be what? Maybe 5. So we can directly reduce this into for all T into Q. Also, if we consider a simple document, a web document or a news document, let's say it will be containing 100 terms. If we want to reduce further, we can also do this as well. So this will be something less than 5, less than or equals to 5. We apply this. Okay. So this factor, so basically if the term is present in the query as well as in the document, we are basically multiplying or considering their product, the term frequencies, the product of their term frequency as the component for the towards the score of the document. So let's say if the query is say Q1, Q2, Q3, then what we are doing is essentially we are doing term frequency of Q1 in Q plus, sorry, into term frequency of the query term Q1 in D plus term frequency of Q2 in Q into term frequency of Q2 in D plus term frequency of Q3 in Q plus multiplication term frequency of Q3 in T. That's it. This summation is considered as the score of the document T. Now consider a collection consisting of tweets as well as Wikipedia articles. So we know the length of the tweets will be maybe say 20 terms max to max, and the length of the Wikipedia article can be 1000. So considering this, the TF of, so this part will be constant or this part will be same for both of them. So basically let's consider a collection containing tweets as well as Wikipedia articles. Now we know in the tweet the occurrence of the query term or occurrence of any term may be once or twice max because it's a short text. But in case of a Wikipedia article, it is a long text. The chance of occurrence of the same term again and again in the Wikipedia article is much higher than in a tweet. So this factor will be much higher for Wikipedia article than tweets. So as a result, tweets will never be, it will be retrieved but never be in the top position, right? So the bottom line of the problem is basically this model that is only considering the weighted, only the term frequency is biased towards longer document, and we need to normalize it by the document length. So far there is no factor of length normalization in this model. So as a third approach, what we'll be doing is we'll be using a normalized term frequency model. So instead of considering the term frequency, we'll be considering a relative term frequency. So what is this? So this is the document factor. This is basically the weight of the query term in D. So instead of considering the raw TF, we will be considering the TF normalized by the document length. Why we are doing this? So let's say in a document, so let's say a document D1 equals to say, I mean, let's say in a document D1, the query term, the term frequency of a query term Q in the document D1 is say 10. And I have made another document D2, which is basically D1 plus D1, concatenation of the D1 with itself. In this case, the term frequency of the same query term in D2 will be how much? I hope you can guess. It's 20. But the length of D1 here is say 100, and the length of D1 or D2, sorry, is here will be 200, right? 100 plus 100. Now, if we consider only the TF, it will be 10 and 20, this factor. But if we divide it by the document length, it will be basically 10 by 100 for D1 and 20 by 200 for D2, which is same, right? This is basically the normalized term frequency. One question to you: why we are not doing the same thing for the query as well? That is, why we are not dividing the term frequency of the query by the query length? Please answer, anyone. Because this I have already discussed. I hope you can remember this. Because our ultimate target is ranking, and the score will be different if we do this, but their relative ranking will be remaining the same because we are doing this for all the documents in the collection. So D1, D2, up to say D1 million. For all the documents, while ranking, we are applying this, this division by this dividing by the query length of the overall score. So the score will be different, but the ranking will be the same. But as we have discussed, IR is all about ranking. That's why we are not actually doing that. Now, in this model, there is no factor of rareness or the importance of individual terms. There is no such indicator other than this term frequency. But we have discussed earlier that rareness can be actually realized by their document frequency. In other words, particularly inverse document frequency is a factor using which we can actually somehow understand the notion of rareness or the discriminative power of a term using the inverse document frequency. So this is the fourth approach, incorporating the inverse document frequency into the picture. Earlier, so in the second approach, the weight was only TF. In the third approach, we divided it by the document length to make it length normalized. In the fourth approach, we are incorporating the IDF factor here. Okay? Where here n is the number of documents in the collection, and df of t is basically the number of documents containing the term t, basically the document frequency. So it gives more weights to the rare terms, this factor. This is basically the inverse document frequency. So finally, for a given query, the document D will be scored as this. Again, this is the factor, or this is the weight of the term, or as I am writing T in Q, and this entire thing is basically the weight of the term in D. So we are considering a TF here for the query and TF IDF here for the document. Now, suppose query term Q occurs twice in doc A and once in doc B. So basically term frequency of Q in document A is 2 and term frequency of the query term Q in doc B is basically 1. So can we say document B is or document A is twice relevant than document B? So here we can overall say this, because more the number of occurrence of the term, more likely that it is relevant. But can we say the same thing for the document A when it is containing 20 times the term occurrence and once in the document B? Can we say that it is 20 times relevant? Definitely we cannot say that. But using the raw term frequency here is basically ensuring that, but basically indicating that. So what we need is a sublinear TF scaling or a sublinear term frequency function. So instead of using a simple, weight as the simple term frequency, what we can do is we can actually use a damping factor like this, like we have seen earlier. So here we will be seeing that it is occurring, or it is incrementing the weight in the y axis. It is basically the relevance or the weight, and in the x axis it is basically the term frequency. So as you can see, it is increasing in the beginning rapidly, but later on the change in weight is kind of normalized or kind of reduced. So using this sublinear TF scaling, we are ending up with the final approach, which is the fifth approach, where instead of using this factor, we are using a sublinear TF scaling here together with the IDF. And following this, this is the weight of the term in the query, and this is the weight of the term in the document. Now, from this diagram, I hope you can remember the Heap's law. So the Heap's law states, as we see more and more text, the frequency of new word, or the chances of new word, the occurrence of a new word which is not already been observed, will decrease. This is basically similar to the Heap's law. So in other words, after the occurrence of the first after the occurrence, after the first, second or third, the earlier occurrence of the term, it is likely that the term will be again occurring. So there is no point in giving it extra advantages or keep on giving it the same advantages for each of the increment or each of the time I am observing the query term. So let's say I am reading one document, a large document. Let's say I have encountered the term here. So I got fascinated. Wow, I have observed this term. The next, I'm observing it, the same term again. The excitement of me seeing the same term will be reduced, will be less. And the third time when this occurrence is observed will be much less. And for the latter occurrences, it will be even lesser. That's why we need to apply this sublinear TF scaling for weighting the terms. So in sum, in the TF-IDF scoring or TF-IDF term weighting, what we are doing is, for a given, so basically we are computing the weight of the term T in the document D based on its term frequency. This can be the scaled one, this can be the normalized one, this can be both, and it is basically multiplied by the inverse document frequency of the term. This is basically common for all the documents, because this is basically a fact. This is basically computed for, I mean, over the entire collection. Now TF will be greater when the term is frequent in the document, and IDF will be greater, that is IDF will be having a higher value when the term is rare in the collection. So we will be observing a higher TF IDF weight if factor 1, if it is occurring or if it is I mean occurring with a frequent higher frequency in the document, or if it is a rare term, that is if the term is occurring very infrequently over the collection. Ideally, a very good discriminating term will be having higher TF, but together with that higher IDF as well. Okay, any question up to this? All right. So as we have said, there is the provision of using the weight of the query together with the weight of the term in the document, right? So, and this can be actually weighted, the discussion that we had just now. This is for the query, weight in the query, this is for the weight in the document of the same term. Now, the smart retrieval model developed by the Cornell University by Gerard Shelton actually made a very nice representation of this term weighting. What this is actually called the smart notation, because it was introduced in the smart retrieval model, or not smart retrieval model but smart search system. So what it says is this, so individual weights, as we have seen, is basically consisting of three factors. One is the term frequency factor, second is the document frequency factor, and third is the length normalization factor, right? So we can apply some of them to some of these weights. It is generally referred to as the DDD-QQQ scheme. This first D is specifying whether I'll be applying the term frequency factor in which way. The second is basically I'll be applying the document frequency for weighting the document in which way. There are three alternatives. And D norm is basically while computing this, whether I'll be applying no normalization, cosine normalization, or anything else. Similarly, while computing this, whether I'll be applying the term frequency, natural, the raw one, the logarithmic one, the augmented one, or something else. Similarly, for document frequency and the normalization. A very standard weighting scheme is basically called LNC LTC, which means while computing the weight of the term in the document, I will be applying this. So let me just use the same color. So for this, I will be using L, that is basically this. That is, I'll be using the logarithmic term frequency, that is 1 plus log TF. I will be using no document frequency at all, so this will not be divided by the document frequency, or there will be no notion of inverse document frequency here applied, and I'll be applying this cosine normalization here. This is for the document, and for the query what I'll be doing is weight of the term in the query will be basically LTC. So LNC is for the document, sorry, LNC, and LTC is for the query. L is again the same, logarithmic 1 plus log TF. I'll be using the T here. I'll be using the normalization, the IDF normalization here. Basically log of n by df, and I'll also be applying this cosine normalization here as well. Now note that although I am applying this at the query end, this is also being applied here. I mean, it is essentially, we can also, in a similar way, we can write LNC LTC can be similar to LTC LNC, because essentially what we are doing is we are weighting the TFI, we are basically computing the weight of the term in D into the weight of the term in Q. So if I apply this IDF normalization here, it is also being applied somewhat here, because ultimately it is just being considered as a score, right? So this is actually a very popular state-of-the-art schema that was very popular earlier. Still, if someone use a vector space model, they use this LNC LTC schema. That's it up to today's class. Any question?